we will embark on the last part of this course, that is the various methods for stability improvement. Before we do that, let us just have a quick look at where we ended last time. We had basically discussed the phenomena of subsynchronous resonance. There is one case study which I ran. So, I will just quickly relook at that, and then we will move on to the next part of this course, that is on stability improvement. So, today's lecture will be primarily on stability improvement. In the previous example, where we studied subsynchronous resonance, we considered the adverse interaction of a series compensated transmission network on the shaft of a generator turbine system. Okay. So, we had done a case study of a steam turbine generator, and where the rotor was represented by a 6 mass system, okay, connected by shafts. So, we had seen that for a certain level of series compensation, there was adverse interaction, and you had growing oscillations for one particular torsional mode. Okay. So, if you look at in fact the eigenvalues which we got for this particular system, we see that torsional mode 3 is very badly affected. In fact, that is what you see in the simulation study as well. We see that particular mode growing with time. Okay. Now, in this particular study, of course, I should mention that we did no damping was no mechanical viscous damping was considered. Okay. So, the only damping which was possible was due to the interaction with the electrical network, and you see that in fact, all the torsional modes seem to have positive real parts. Okay. In actual practice, there will be some viscous damping, and some of these modes actually torsional mode 1, 2, 4 and 5 would be stable if one considered that viscous damping typically. But torsional mode 3 has got a very large positive real part, and you see that it could cause a real problem in the system. Okay. So, if you have got this kind of situation, that is you have got a subsynchronous network mode due to series compensation, and typically if you have a situation where the network mode frequency coincides with the torsional mode frequency, this problem could occur. Okay. Now, of course, there are a few more qualifications to this statement. It is assumed that the electrical torque can affect the torsional modes, all torsional modes. This need not be true. In fact, the electrical torque is actually applied at the generator mass. Okay. That may not actually kind of control or affect all torsional modes. In fact, in this system, torsional mode 5, it turns out, is hardly affected by the presence of the network mode, okay, subsynchronous network mode. So, in fact, although this is not really, we have not proved this, or I have not really proved this to you, but it actually turns out that in this particular case, this is true. Okay. So, it is not certainly true that if you have got a series compensated network, it should affect all torsional modes equally, okay, and it depends on how much the electrical torque affects a particular mode. So, that actually kind of analysis can be done using our eigenvector and eigenvalue analysis. Okay. Now, there are some other situations which we need to, the last word has not been said on this. For example, in a practical situation, you can have several series compensated lines. This is one possibility. You got 1, 2, 3, 4, 5, 6 series compensated lines in this network and several generators. Okay. And each generator, what I have shown here is generators, these round things are generators, themselves may be actually several units of a power plant. Okay. It need not be one generator here. Okay. So, in fact, you can have many subsynchronous network modes, and you can have many torsional modes, and you actually have to do a kind of a linearized analysis to check out the actual effect of all these network modes on individual turbine generator shafts. Okay. Normally, as I mentioned some time back, hydro turbines have a relatively large generator a very large generator mass compared to the turbine mass. Okay. This is not true in fact for steam turbine generators. So, in such a situation, one can what really happens is that the electrical torque does not have that much controllability over the torsional modes. These are all statements which of course, I am making without much proof. In this course, it is out of the scope of this course to discuss these things in too much detail, it will take a very long time. So, I request you to go through the literature on this subject, especially the kind of discussions which are given in Padiyar's book and Kundur's book. Okay. In fact, for this particular system where I have shown 6 series compensated lines, just to give you an idea, you have got 6 series subsynchronous network modes. Of course, there are other network modes, there are other modes as well, but I have just written down the subsynchronous network modes. Okay. Now, this kind of analysis can be done with the tools which I have already discussed in this course. So, in principle, you should be able to formulate the equations of this multi machine system, each generator having several rotor masses, and it should be possible to do a kind of linearized analysis. Okay. Remember, it is a nonlinear system. So, you can simulate the nonlinear system, but if you want to do a linear analysis, you have to linearize the system around an equilibrium point. Okay. So, this is one of the things which I wanted to discuss before we go on before we take on the new topic. Okay. So, with this I kind of end my discussion of subsynchronous resonance, the phenomena of subsynchronous resonance. Remember one thing, of course, how can you avoid subsynchronous resonance? One of the ways it appears you can do that is to prevent a coincidence of a network mode with a torsional mode. Remember that if there is no coincidence, the effect on the other torsional modes is quite low. Okay. See, torsional mode 1, 2 and 4, the adverse interaction is quite low. Okay. And one would expect that if mechanical viscous damping is present, these modes would actually be stable. Okay. Problem comes in torsional mode 3 where there is a good coincidence. So, it would make sense to limit the series compensation in a transmission line such that it avoids coincidence of coincidence with the torsional mode, and this usually can be done if you try to design your series compensation so that the network mode frequency is higher, okay, significantly higher than the highest torsional mode frequency, which is controllable by the electrical torque. So, in this case you should limit fixed series compensation in the form of fixed capacitors such that the network mode frequency is higher than this 202 radian per second. So, you need to you can't have a very large XC. Okay. You can easily prove that this subsynchronous network mode frequency reduces. This of course, the equations are formulated in the DQ reference frame, remember. The subsynchronous frequency reduces if the equations are formulated in the DQ frame, if XC, that is the series compensation, the reactance corresponding to the series compensation increases. Okay. So, one may actually have to limit the amount of series compensation, so that there is no torsional mode and network mode coincidence. In fact, this actually tells you an important thing, that stability issues in certain conditions can restrict what you can do with the system. In fact, if you recall, I had mentioned that series compensation is something you do to reduce the reactance, the series reactance of the transmission network. This in turn improves the power transmission capability of a transmission line, because it reduces X of the transmission line. If it reduces X, you can improve, you can have better large disturbance stability characteristics. Okay. So, because of this SSR problems, under certain situations, okay, you may have to limit the amount of series compensation you can have. Okay. So, stability problems sometimes can be a limiting factor in the design, okay, of your system. So, now let us end the discussion on this topic and move on to what our next and last topic is, that is improvement of the stability of a system. Okay. So, the whole idea of doing this analysis was to see how it affects a real power system. Okay. So, just to keep things in perspective, the first part of our course dealt with analysis, a generalized analysis of dynamical systems. Then we spent quite a bit of time on modeling of synchronous machines, excitation systems, loads, prime movers. You would like probably to go back and have a look at these, some of the simulations and all which I carried out when I was discussing these topics. Then we also discussed how you can model a transmission line. The part B of this course, we discussed several stability issues. One was the motion of common frequency, that is the center of inertia frequency of the system, which is in fact affected by the load generation balance in the system. Then we also discussed the probably the most important problem in synchronously connected systems, that is when you have got synchronous machines connected by AC transmission lines. The most important problem, stability problem, is in fact the relative angle or the relative frequency motion. Okay. And we discussed things like loss of synchronism, etc., under the topic of relative angle movement and frequency movement. Okay. Then we also discussed voltage stability. We took an example of voltage stability. We in fact studied slow voltage instability caused by the action of tap changing transformers and reactive power limits in a synchronous generator. The last topic which we just kind of ended the discussion some time back was on shaft torsion, the stability of shaft torsional oscillations. Okay. We also actually merged, we did not consider this as actually, although I had listed it as a separate topic, we have in fact discussed or actually done a few simulations, and there are two kinds of simulations we did. One in which we considered network transients and stator flux transients, and the other in which we did not consider it. The studies in which we do not consider network transients, the stator flux transients, are called transient stability programs, because these are really low frequency phenomena, rather suited for the study of low frequency phenomena. And EMTP kind of programs in fact have to model fast transients in detail. We also did side by side an eigenvalue analysis in many cases. Okay. But eigenvalue analysis, remember, requires linearization of the system in case your system is non-linear. Okay. We now move on to enhancing system stability, and in this context it will be I think appropriate to consider this from T.S. Written by kind of quote written by T.S. Eliot. We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and to know the place for the first time. So, in fact, when I am talking about the topic of stability improvement, when I will be discussing this topic, we have done all these phenomena before. The first phenomena in fact I will be considering is under frequency relaying, stability improvement measures. We have actually discussed this issue of under frequency or over frequency, which results because of load generation imbalance. Okay. So, we have done all these things before. Now, we shall focus on trying to see how we can actually improve stability of the system. So, let us take the simplest phenomena, that is of frequency stability. Frequency stability is easy to understand. We saw that the movement of the center of inertia of a multi-machine system, okay, is dependent on the load generation balance, and the controls which affect this are effectively the speed governors which may be present on the turbine of a synchronous generator. Okay. So, the main control by which we can actually affect the frequency of a system or ensure that the frequency remains within limits is essentially a governing action of steam or hydro turbines, okay, or gas turbines. Now, in addition to governors, remember that the loads themselves are frequency dependent, but that frequency dependence is not very strong. Okay. So, if you do not have governors and there is a load generation imbalance, the frequency changes and it settles down because the loads themselves are a function of frequency. Okay. But say in our system, which is around 150 gigawatt, it is a 150 gigawatt system of installed capacity, a 100 megawatt change may cause say 0.1 hertz change in the frequency, okay, in case there is no governors. If there are no governors, just because of load frequency dependence, okay, you can come to an equilibrium, which is reasonably which is acceptable if the load generation imbalance is low. Okay. But if there is a, say, a sudden generation trip of 1000 megawatts, okay, then just depending on load frequency dependence to get you to an equilibrium is not appropriate, because the frequency deviation can be very large. And remember, we had discussed this before, that if frequency deviation is large, many turbines will have to be tripped out, because typically under off nominal frequency there is a danger of exciting shaft torsional vibration, not shaft torsion vibration, sorry, blade vibrations in the turbine. Okay. So, if there is a frequency deviation of more than 1.5 hertz or so, you may have to quickly trip out your turbine. So, actually a blackout can ensue in case your frequency of your grid falls below, say, 47.5 in a 50 hertz system. Okay. So, this is in fact an important consideration. So, in fact, along with governors and the effect of load, load frequency, low frequency dependence, another way of ensuring that frequency does not go to perilous kind of levels is having some kind of under frequency, or these are emergency controls. If the primary control in the form of governors etc., is not able to arrest frequency drop, okay, in that case you may consider using under frequency relays, or in fact rate of change of frequency relays in trying to arrest this decline. So, let me just show you an actual event which occurred in our Indian grid several years, about a year ago. This is 8th August 2009. There was a generation trip at a generator at Anpara, that is in Uttar Pradesh, and the effects of it surprisingly were immediately felt. Okay. Not surprisingly, we know that frequency everywhere in the grid is practically the same. Okay. It is not really surprising, but something to wonder about it. It really evokes quite a bit of wonder that immediately you see a frequency decline in Mumbai, Sangli and Surat, because these parts of the grid are synchronously connected to the grid in Uttar Pradesh, which is more than 1000 kilometers away. So, there was a generation trip in the synchronous grid, and the frequency drops everywhere in the grid, including the western region, and you see this quite a precipitous drop in frequency, okay? A very high rate of change of drop frequency. And if you just allow this to go on, okay, then the frequency can go down, right down, and cause a tripping of all turbines, all the steam turbines in the system, and there could be a blackout. So, what you have is some kind of control action here seems to have reduced the rate of drop, and at around 48.8 there seems to have been some load relief in the form of under frequency relaying. So, at this point the frequency has dropped down, and in the system you have got certain loads which are designed to trip, or rather there are protect relays which are designed to trip out these loads in case the frequency falls, and this is exactly what has occurred at this point here. And of course, after the load is tripped, the frequency rises again. Okay. So, in fact, if you look at this a bit carefully, there is a generation trip occurring here, there appears to be another generator trip out here. This is an event which occurred about a year back, and it seems that there has been, if you look at this, there is a sudden slope change at this point. So, there was some load relief even at this point. So, there are actually two, you have got a load relief somewhere here, and you have got under frequency load relief even at this point. So, this is what is probably been designed in the grid to, it is a kind of emergency control in the grid. Okay. Now, you can, instead of having plain under frequency relaying, in case there is a trip in generation, you will find that the frequency drops, you can kind of measure the rate of change of frequency at various buses. In fact, this is the rate of change of frequency at various buses after a generator trip. This is a simulated response of a multi-machine system, and you see that there is a the center of inertia frequency goes on dipping Okay. Now, you can use this rate of change information also to do some quick control action. Okay. Now, if you even look at plain under frequency relaying, what is plain under frequency relaying? If the frequency falls below a certain value, you trip out certain loads. That is basically what happens here. Okay. Frequency falls, you trip out load. Now, if you look at the issues behind which have to be considered when designing an under frequency scheme, they are as follows. First thing, how much load do you trip? At what frequency do you trip? Okay. Remember, load comes in chunks. Okay. So, you have to trip out a certain amount of load if the frequency falls below a certain value. Now, which value should you choose? Okay. Another point is how much you trip. If you trip too much, you trip too many loads, say you trip out the loads at several small towns or cities, small cities in the country, okay, say to get a kind of load relief of say 600 or 700 megawatt, then the point is how much, how much load do you actually trip. If you trip too much, you will find that you may have an over frequency situation. Okay. So, the point really is that this kind of design of an emergency control system is often carried out based on offline studies. So, you kind of do an offline study based on the parameters of the system and see, if I trip this much load, how much frequency rise will be there. Okay. But this is obviously, since it is an offline study, it is based on some our knowledge of the parameters of the system. Okay. But if you do not have adequate knowledge of the parameters of the system, design of this may be quite tricky. In fact, under normal operation, you will find that the operating condition which you have under a normal say today right now may be difficult to anticipate during planning. Okay. But roughly you can get a operating point close to what the situation is. When I say what is the operating point today, basically the generation schedule, the load at various points actually changes from day to day, from hour to hour, okay, and it depends on the season as well. Okay. So, during planning you have to kind of anticipate the kind of load pattern and the generation pattern in the grid, and design how much load would need to be tripped in case the frequency fell below a certain value. Okay. So, this is how you design your under frequency relaying scheme. Obviously, it is not a perfect science. Okay. So, as I was saying, instead of plain under frequency relaying, you can even think of df by dt relaying. df by dt relaying is basically checking out the derivative or the rate of frequency drop, okay, at a bus, and then take a decision of whether to trip or not to trip. Okay. So, these schemes also have to be designed at a planning stage, but remember, df by dt is a kind of an anticipatory scheme, in the sense that if the rate of change of frequency exceeds a certain value, then you trip out certain predetermined loads. So, it is a kind of anticipatory, but it is again designed offline, and the things you need to really consider in your design is what exactly affects the rate of change of frequency. In fact, if you remember, the center of inertia frequency of the system, the rate of change of the center of inertia frequency of the system is inversely proportional to the sum of the machine inertias. Okay. The other thing which determines df by dt is the amount of load generation imbalance. So, if the load generation imbalance is large, you will have a larger rate of change. Of course, so by looking at df by dt at a particular bus, the bus frequency as it falls, you can roughly make out whether the disturbance is large or small. Okay. Now, there are of course, again design issues of how much load to trip, where do you trip, okay, and so design of this aspect is usually done offline. Okay. But if you really look at some let us just look at some important aspects which you need to consider when you design a df by dt relaying scheme. Remember that although I have said that the center of inertia frequency depends on the load generation imbalance, remember that local frequency or frequency of an individual generator is often contaminated or it contains swings as well. So, what you see for example, is the frequency of all generators or the frequency at various buses in the system. You will see that not only is there a kind of a common motion, there is also these swings. And interestingly, there are many swings. You see that there is one relatively low frequency swing here, then there is a higher frequency swing here. Okay. So, there seems to be a mixture of swings along with superimposed with the center of inertia or the common motion of this system. Okay. So, these of course, these swings are something we have discussed before. They arise due to the power oscillation or the motion of or the relative motion between generators. Okay. So, in fact, we had done simulation of a single machine connected to an infinite bus, then we had also done simulation of a two machine system, and what you noticed there was, in addition to the common motion which depends on the load generation balance, there is also the motion, relative motion of speeds and angles, rotor angles of individual machines. Okay. If you have got a large multi machine system, this is not a large multi machine system, but just to illustrate, in a large multi machine system you can have oscillations between the machines within a plant or the machines, the oscillation between a machine in the same area or a machine nearby against the machines in a plant all moving together. So, you have got in an intra-plant mode, only the machines within a plant participate and they swing against each other. Okay. They swing against each other. Then you can have this local mode in which these two machines swing together with respect to this machine in the same area, or you can have all these machines in an area swinging together against the machines in another area. Okay. So, in fact, if you look at this simulated response, you will find, in fact, if you look closely enough, you have got some machines which are swinging together, okay, against machines in another area. Okay. If you look at this real life picture of how the frequency changes, you see that the frequencies measured at Mumbai, Sangli, Surat, which are all in one area, okay, seem to swing together here. You see this small oscillation here, there are minor oscillations here, swings which you see. Okay. These are actually, and for this particular mode which is visible, oscillatory mode which is visible, all these machines swing together. This is not actually a surprise, this disturbance occurred very far away from these locations which are in the western system, and therefore, all the machines in this area swing together. So, this is intuitively makes sense. Okay. So, whenever you are going for df by dt relaying, you have to face one problem, that is, in addition to the common motion, there are also these swings. So, that may actually give a completely complicated picture of. So, if I take the derivative of the frequency, this is what I see. Okay. So, if I see this, I may actually have spurious tripping, because because the slope at some points may be large because of the swings and not because of the common motion. Okay. So, this is one problem which you may face if you are going to have local frequency measurement. So, if I take a frequency at one particular point and try to take a local decision whether to trip a load or not, I may actually have a problem, because the local frequency actually has got these swings. Okay. And because of that, I may get a wrong information or spurious information about load generation imbalance in the system. Okay. So, this is one of the problematic issues when you try to apply a stability improvement method like under frequency or df by dt relaying. But one may suggest at this point that why do not we actually compute the center of inertia speed. Remember, we had got this formula. Okay. So, we had actually derived this formula sometime back in our course, that the center of inertia motion depends on, is proportional to the sum of the mechanical, total mechanical input to all generators minus the total load minus the losses. Okay. That is because sigma P e is equal to sigma P L plus losses. Okay. This is of course with network transients neglected. This is true if network transients are neglected. Electrical power output of a generator is equal to, under sinusoidal steady state conditions, sigma P L plus losses. We are considering a slow phenomena. So, we do not have to consider network transients in our analysis. So, this is certainly true. Okay. So, the point is that suppose there is some disturbance, okay, and now you want to trip load to control the drop in the center of inertia frequency or the common motion. Okay. You want to prevent a precipitous drop. So, you want to do some load shedding. Now, what one can do is try to compute omega COI, okay, and then because you know omega COI, you can compute this rate of this particular term, okay, and because of this you can estimate what this imbalance is. So, I will call this imbalance. So, depending on this imbalance you can then decide to trip certain loads to bring back balance, okay, in case there is a drop in frequency. Okay. But what is the catch in all this? The good thing of course in doing this particular this kind of computation is, unlike frequency, local frequency measured at every bus or at every generator which is contaminated by these oscillations, okay, which may kind of blur the common motion. A minor error here, the y axis is the rate of change of the center of inertia frequency. It is wrongly indicated in this figure as the center of inertia frequency itself. So, remember the y axis label should read rate of change of center of inertia frequency. So, what you are seeing in this graph is in fact the rate of change of center of inertia frequency. The center of inertia speed is somewhat, ink component you see here is relatively lesser than what you will see here. Okay. So, you can use the rate of change of the center of inertia speed, but what is the catch? The catch is that this omega COI is not a local signal. First of all, you will have to take out the speeds of all the generators, okay, then use the speeds of all the generators to compute this. Remember that speed of generators is time varying. So, you have to get the speed of the generators at kind of to a common point and then compute this particular thing. Okay. So, this requires some communication of signals. Similarly, if there is imbalance, so if you estimate the imbalance, you will have to send a trip signal to a remote location and trip out the thing. So, this seems nice. I mean, as engineers it sounds like a nice challenge to really make a wide area measurement scheme of a frequency or speeds of all generators, compute this, okay, and then do this kind of thing. So, this is just, of course, this is not implemented anywhere in the world, but this is an interesting thing you can do, and as students also you can easily conceptualize this kind of thing. But remember, things are not as easy as they look. Remember that the power system is spread over tens of thousands of square kilometers, and you need to communicate quickly. You do not want too many delays in all this. You have to quickly communicate this signal to a common place where this computation is done, and this computation has to be done, and then you have to estimate the load generation imbalance, and then you have to choose a suitable chunk of load. Remember, load comes in chunks. So, you have to choose a suitable chunk of load which you can trip, okay, to get the frequency back to normal. Okay. Now, of course, there are several important points which have to be considered at this point, is that when you have got a synchronous grid, typically this very precipitous kind of drop in frequency occurs when you have got an interconnected grid. Okay. Suppose you have got an interconnected grid which has got connections with AC lines. There are two areas, suppose. Okay. One area has got say 10 gigawatt generation and 11 gigawatt load, and the other generation region has got 11 gigawatt generation and 10 gigawatt load. Okay, we will assume losses are negligible. In that case, if because of say some disturbance there is a loss of synchronism and you separate out these two systems, then this system will be an under generated island. Okay, there is a load generation imbalance and you will have to trip out this load, some load, to get this load generation balance. So, one of the ways you can really do it is compute the center of inertia of the, now once you separate out, you just have, you have to compute the center of inertia speed of this particular system. So, something which your central computer which is computing the center of inertia needs to know is which are the generators in this island. Okay. So, you need to know that. So, this is one issue. The other thing is the speed of all the generators in this island need to be computed in a synchronous way, in the sense that they should be time tagged and sent to a common center, at which they are all after all omega C O I t is sigma h I omega I t by sigma h I. You need to know the generator speeds of all generators in that island at the same instant of time, in order to get the center of inertia at that point of time. So, you need to time tag all the frequency measurements, send them to a common location and compute this for every time time instant, okay, and then take out the derivative and then do df by dt relaying. Okay. So, this is one particular scheme you can do this, which you can use proper technology and actually compute this and derive a good scheme for under frequency relaying. Okay. So, this particular scheme is not implemented, but it turns out that today it is feasible to do this. Although there are issues, as I mentioned some time back, you should know whether there is an island, which generators are part of the synchronous grid and which are not, and so on. So, there are still some issues which need to be considered before such a scheme can be actually put into action. But today it turns out that it is feasible to have time synchronized, very well time synchronized measurements using GPS satellites. So, you can actually measure the frequency or generator speeds at various locations, time tag them. Okay. All the measurement units here, these are called phasor measurement units, are all synchronized, having the same kind of synchronized clocks by using GPS, GPS signals you make. All these have synchronized clocks, so that the time stamp, the frequency or generator speeds are time stamped and sent to a common load dispatch center, wherein the center of inertia speed in principle can be calculated, and then you can use these signals to trip out certain loads. Okay. So, in principle this kind of scheme is feasible. The reason why I have discussed this kind of a scheme is not because I have not done a kind of a rigorous analysis of the feasibility of such a scheme or anything of that kind, just to spur you to think that you can actually use technology and actually implement these kind of things. In principle it is possible. Okay. But of course, as I have cautioned and I will caution you again, there are many engineering issues which need to be dealt with before you kind of make this kind of scheme. Okay. It is called an emergency control scheme. Okay. So, I have kind of introduced you to a way by which you can have a method for improving stability. In this particular case, we are talking of improving the frequency stability of a system. So, we have talked of under frequency relaying to prevent sudden drops, which may occur when there is a sudden load generation imbalance because of generator trip or sudden islanding, okay, because of loss of synchronism, which is another stability phenomena we will just discuss a bit later. Okay. Now, if you have got two systems which are not connected synchronously with each other, that is, they are connected via HVDC links. So, the frequency and phase angles of system A and B need not be the same. Okay. The frequency here F A and here F B need not be the same. Okay. The power through this link is regulated strictly. Okay. In this situation, in case there is a precipitous fall of frequency here, or in fact there is even a rise of frequency, sudden rise of frequency because of a major load trip. Okay. In that case, you could ramp up the power. Suppose there is, for example, a sudden very large load trip in this system, okay, because of which the frequency tends to rise, and the governors here are unable to prevent a sudden, the rate of change of frequency or the frequency rise is very fast, and the governors are not able to control it, okay, because say the limits of the turbines, etc., they are not able to control it. In that case, you can use, for example, an HVDC link to temporarily pump some power out of this, okay, pump some power out of this and push it into this, okay. But the frequency here will rise, remember, because of that, okay. But rather than have a very large rise in one system, you can use this particular HVDC link to ramp the power and push that power here, okay, and kind of distribute this frequency change. Okay. This kind of also scheme can be kind of developed. Remember that in an asynchronous link, each area the generation is equal to sum of loads plus losses, and similarly P g here will be equal to sum of load plus losses plus minus P HVDC, and this will be plus P HVDC. Remember, P HVDC is completely controlled in a local fashion by this rectifier and inverter here. Okay. So, you can actually add the link itself can regulate power flow because you have got firing angle control. So, in some cases you can change HVDC power, okay, and control the frequency, but you cannot do independent frequency control in both regions. If you change the HVDC power, this will get affected and this will get affected. Okay. So, this is just to kind of tell you that kind of encourage you to think of all these things. Okay. Yeah. So, this is when you have got an asynchronous link, asynchronous connection between two regions. Okay. So, you can use HVDC power to equalize or slightly help one region, okay, by changing the HVDC power. Please note that there is a minor error in the sign here. So, this should be positive here and negative here, okay, if the direction of HVDC flow is as shown in the figure here. We now move on to a more worrisome problem, or not even frequency change is a sudden frequency changes are a worrisome problem, but a more commonly felt problem for which understanding what needs to be done is not very obvious. Okay. Now, let us to kind of get a very clear picture of what we are talking about. Remember that just a few moments ago I was talking of this problem. If there is a sudden load throw off or a sudden generator trip and governor action load frequency dependence is inadequate, you can have maybe stable common motion, but the frequency change may be too high or too low, or rather the frequency change may be too large in magnitude, and therefore, you may think of emergency schemes like load tripping schemes, okay, or the converse of that is generator tripping schemes. Okay. Of course, generator trip is something which you have to be careful while doing, because a fully loaded generator, if you suddenly trip to prevent an over frequency, it gives a big shock to the mechanical elements of your system. Okay. That is the turbine generator system, the turbines mainly. Okay. So, generation trip is not often talked in the same breath as load tripping. Load tripping is somewhat more benign compared to tripping a fully loaded generator. Okay. So, these are the things which you need to do in case there is a large magnitude of frequency change, the common frequency change. Okay. But you may have unstable relative motion as well. For example, The figure which I am pointing out here shows the generator speeds for relative angle instability in which there is a loss of synchronism, that is, the machines are connected, but a couple of machines here run at a different frequency compared to the other. So, this happens whenever you give a large disturbance like a fault. Okay. This can happen for large disturbance like a fault, wherein synchronous machines which normally run at the same speed, because of the fault suddenly lose synchronism. This is a large disturbance phenomena. Another problem which may arise with relative motion is that the power swings or the low frequency oscillations which we see following even a small disturbance sometimes may be poorly damped or even grow with time. Okay. This is a more complicated problem in the sense that even so small disturbances, sometimes you see that the oscillations which are triggered take a very long time to damp out, or in some situations they may even be unstable. Okay. So, this kind of situation can occur under certain situations. Okay. So, let us I will just show you the phenomena and then we will end this particular lecture. We have done this simulation some time back. We had done a Scilab simulation in which, if you recall, this is a Scilab simulation. I have actually changed the program. So, let me save this. This is a program which simulates a synchronous machine connected to an infinite bus. Okay. The field voltage of the synchronous generator is actually being controlled by the automatic voltage regulator. Okay. And what I am going to simulate is the response of the system for small disturbances around an equilibrium point. So, what we have got, so the simulation which I will just show you before we end today's lecture is you have got a synchronous machine which is connected via a transmission line to a fixed voltage source. We call this an infinite bus of frequency omega naught. The machine is assumed to be operating at a mechanical power output of 0.5, which is equal to the electrical power output in per unit. Okay. This generator is equipped with an AVR, which maintains the terminal voltage of the generator means almost at a constant value. The AVR basically has a structure Vref, V, a proportional controller, and this is the voltage which effectively is through a static excitation system applied to the field, which creates the which really creates the field flux. Okay. So, by having this kind of control system, you are controlling the field voltage and therefore, you are kind of almost meant, if this K is large, you practically are regulating this voltage V to a constant value, which is almost equal to Vref. Okay. So, we have done this simulation before. What I will do is assume that the system is operating at this operating point. Okay. So, when I am simulating, what I need to do is specify the terminal conditions, okay, specify the power output. From that, you can back calculate the current. If you know the reactance of the line, the resistance of the line, you can back calculate the current output of the generator and back calculate all the initial states of the generator. Okay. Now, if the initial states of the generator are those corresponding to this kind of scenario, equilibrium scenario, the system will simply remain where it is. Okay. Now, thereafter, what I will do is give a small disturbance here. What I will do is I will increase Vref at 5 seconds for a short while and dip it back. Okay. So, I will do that and then we will see what happens. Now, just to keep things in perspective, what you need to do is of course simulate. What we are going to do is simulate the system. So, you have to feed in the data. We will give Tm is equal to 0.5 per unit. This is the gain and time constant of the AVR. Thereafter, we specify the infinite bus voltage magnitude, we assume that the infinite bus voltage angle is 0. Okay. Thereafter, we calculate theta, which is the phase angle of the terminal voltage of the synchronous machine. Okay. This is obtained by, we will also specify, we have already specified what T m is. In equilibrium conditions, P m is equal to T m is equal to P e is equal to T e. There is the torque and the powers are the same, with the assumption that the infinite bus voltage frequency is the same as the base frequency. Okay. After that, we calculate the initial conditions, the steady state values, okay, and then we do a simulation. The simulation of course, will remain, if we have calculated the values of the states to be equal to those corresponding to equilibrium values, we will just stay where we are. Okay. So, we will just stay where we are, and at t is equal to 5 seconds, we will give a step change to V ref. Okay. After 0.5 seconds, we will get it back to its old value. Okay. So, if I simulate this system, so I will just run this simulation. If I run this simulation and plot time versus P e, the electrical power output of the generator, we will just see what it is called, it is P, sorry. So, this is taking some time to simulate, because we are using Euler method. We can afford to use Euler method, because we have in this particular simulation, we have kind of removed the stiffness from the equations using by neglecting the stator flux d by dt's. Okay. That is psi d by d psi d by dt is set equal to 0 and d psi q by dt is set equal to 0. Okay. And remember, another thing is that we ought to use of course more accurate method, like even though we are using an explicit method, it would have been better if we would have used Runge-Kutta method, which is a higher order method, but instead we are using Euler method with a smaller time step. Okay. So, do not do this for real life problems. It is better to use a better method like RK fourth order. I have just used Euler method for illustration, okay, because it is easy to program. Okay. So, for the first time, it is not a bad idea. Now, what I have done is, electrical power is 0.5 and at 5 seconds I give a step change in V ref. If you give a change in V ref, actually it is a pulse change in V ref, which starts at 5 and ends at 5.5, but it excites, because there is a disturbance like a pulse, it excites the swing mode, and you see that the swing mode eventually of course does die out with time. So, this is how the swing mode you would like it to behave. Okay. Now, the thing is that if I change the operating condition, a very interesting thing occurs. So, I change this operating condition from 0.5 to 0.8. So, we will assume that the operating scenario is such that your output of the generator is 0.8 per unit. Okay. So, we are at a different operating point, we do the simulation from that point onwards. Okay. So, I execute this program again, and if you plot, okay, while this is executing, let me just reiterate that we are assuming a different operating point, calculating the equilibrium conditions of the state corresponding to that equilibrium point, then giving a pulse change in V ref. So, the system gets pushed out from its equilibrium, okay, but it is a pulse change. We get the V ref back to its old value. So, what we are doing is, because of this pulse change, the system gets shaken out of its equilibrium conditions, the states move away from the equilibrium conditions, and once the disturbance disappears, the system attempts to, well, we have to see whether the system comes back to the equilibrium again or not. In the previous case where T m was 0.5, this actually happened, okay. But now let us see whether it will happen when T m is 0.8. Okay. What you notice here of course is not this. What you notice is that when you give a disturbance, the system gets shaken out of its equilibrium, but it does not come back to its original equilibrium point. It just goes on oscillating, and this oscillation grows with time. In fact, this occurs under certain operating conditions only and for certain AVR parameters. Okay. So, but this is a distinct possibility, and this in fact has been observed in real power systems. So, in the next class we will try to see how this poorly damped oscillation or in fact growing oscillations can be damped by appropriate control systems. So, this is another aspect of improving stability which we will discuss in the next class.